Hello, and welcome to the Current Science and Technology podcast from the Museum of Science in Boston. I'm your host, Susan Heilman, and every week we bring you interviews with guest researchers and our museum staff covering science and technology in depth. Electrical power is such a part of our everyday lives that we hardly really think about it until it's missing. To talk about the need to store electricity when we're using it less and use it when we need more of it is the museum's Corrine Tate. Hi, Corrine.
Hi, Susan.
So where exactly does our electricity or our energy come from?
Energy is delivered to our homes through our power distribution grid. Basically, the power plants, the transmission lines, the distribution lines, all of that get energy to our homes. But we have problems with our grid. And one of the issues is that our demand for energy fluctuates. It's not constant. We use a lot more during the day when most people are working and less at night when most people are asleep. Same with in the summertime. We use a lot more on a very hot summer day when people are using air conditioning than we do on a cool October day. So even with those fluctuations, we actually still have to build our grid to meet that peak demand, that huge amount of energy we use on the hottest day of the hottest heat wave of summer. But most of the time, we don't actually use that peak amount of energy. We use much less. On average, we might use maybe 60% of that. But we still have to build our grid to handle that peak amount. That means we have a lot of power plants and transmission lines and transformers that are actually going unused most of the time. And that's a big waste.
But what could we do any differently? I mean, we have to plan for those peak times, even though we are using it less. So what's the alternative?
Well, if we were better at storing energy, we could get away with building only what we need most of that time, that 60%, for example. And whenever demand would peak and threaten to overwhelm our grid, we could use that stored energy instead. And when demand is low, we could use that extra energy to recharge our energy storage.
So right now we just create the energy and then immediately use it? There aren't batteries to store any of these things?
No, and actually what we have are called peaking power plants. So we have our base load power plants that provide most of the energy we use all the time, but we have these extra power plants that we only fire up when we need them. So most of the time, they're actually unused.
So it does sound kind of like a waste.
It is. It's actually pretty inefficient. The problem, though, is that up until recently, it's been cheaper to build those extra power plants than it has been to use batteries because the battery technologies we have now are really expensive or they're not long-lasting enough.
So basically we would want to take any extra electricity generated and put it in a large battery, a large storage area. But those batteries, they don't hold the charge or they don't last long enough? Or can they even store enough?
Well, right now, we just don't use batteries for that purpose very much because, first of all, they're expensive. But secondly, a battery for the grid needs to be able to hold a huge amount of power, and you need to be able to charge and discharge it very, very quickly. It needs to be able to release its energy quickly and then recharge it quickly. And basically, you need to be able to recharge it thousands of times, and we don't have really good batteries to do that.
Right. A lot of regular batteries, rechargeable batteries, only have a finite life.
And there's actually one more need for batteries, and that's renewable energy sources like wind and solar. For example, we can get a lot of energy from wind and solar, but it's variable. We can't control when it's sunny or windy, and when it's sunny and windy, it might not meet up with our peak energy demand. So that's another case where we really need good energy storage so we can even out that supply and make use of renewable energy sources.
So today we're going to take a look at some new research that's working on making these large batteries that can be charged up, discharged to be used in our regular electrical grid and with renewable energy electricity.
So there has been a lot of research into making these advanced, long-lasting batteries cheaper. And one of the main innovations in extending battery life is to make the electrodes out of nanomaterials. That means super tiny structures that have lots of surface area. And by dramatically increasing the surface area of electrodes, which is where you charge and discharge your battery, that's where the electrochemical reaction happens. With lots of surface area, it can be more spread out so you don't degrade the electrodes as quickly, and your battery will last a whole lot longer.
Can it also hold more charge because there's more surface area?
I mean, that's another benefit to more surface area is that you can not just recharge it very quickly, but you could also release large amounts of energy pretty quickly too. So that's another benefit of the large surface area of the electrodes.
What kind of materials are they using?
This research was done at Stanford University, led by Yi Cui, a materials science professor there. And the nanomaterials they're using nanoparticles that contain iron and copper. And those nanoparticles are coated on a cloth-like carbon material. Now, those form the electrodes, and they immerse it in an electrolyte solution, in this case, potassium. So the battery chemistry that they're using basically uses cheap, relatively abundant materials, but the idea is similar to what you have in a lithium-ion battery. You're moving sodium and potassium ions between electrodes during charging and discharging. But these materials that he's using allow us to do that more cheaply, and it's also a water-based electrolyte solution, which makes it easier than batteries that use organic solvent-based electrolytes.
Right, so we're talking about cheaper, which was one of the big problems with making these storage batteries, and then also the increased surface area. That's also another added bonus, being able to charge and discharge quickly. So how good is this battery going to be? How long is it going to be able to last?
Well, it seems to be incredibly efficient. They've shown that you can recharge it 40,000 times without losing much capacity. And that's in comparison to lead-acid batteries, which are basically our car batteries. Those can be recharged a few hundred times before losing capacity. And lithium-ion batteries, for example, like our cell phone, those typically last about 1,000 cycles. So this is a dramatic improvement over the other types of battery technologies that we have.
So before we talk about when this might actually be used, I'm curious as to how this would fit into our current grid.
We're talking about charging and discharging these things at least once a day or possibly multiple times a day. So it's going to be something that needs to cycle really often. And we'd probably have the batteries in a few different locations. One would be some of these big power plants where we're generating a lot of our energy, but we'd probably also want some battery storage where it's being used or where our energy is being used at homes and businesses, so we don't necessarily need to kind of have all that extra infrastructure distributing that energy during those real high peak times.
Would that maybe be in place of like a generator to have, like an emergency generator?
Exactly. And for these types of applications, you don't need your battery to be small or light like we do, for example, for electronics or in a car. They can be big and bulky. We really just need them to be relatively cheap, and we need them to be able to charge and discharge literally thousands of times. And this technology seems capable of doing that. It seems like a really great material to use for that application.
So how close are we to actually being able to use some of these batteries in an everyday situation?
We're not quite there yet. It's still relatively in the early phase. Cui's team mostly demonstrated that these electrodes work, that we can charge and discharge them 40,000 times without losing this capacity. But they're still fine-tuning the chemistry, and they're working on making prototype batteries. They've really just kind of worked out the electrode piece of it. So the next part is they're making these prototype batteries to test out.
But at the very fundamental level, they're using cheap and easier to get materials, and they can do the charge-discharge. So now it's just fine-tuning and making it work for a production level.
That's right.
Well, that sounds really great. I would be really happy to not have those blackouts or brownouts in those, peak high heat days in the middle of August here. So thank you very much for telling us about this new nanomaterial battery.
Thanks, Susan.
That's it for this week's show, but be sure to come back next time for more of the latest in science and technology. This podcast is a production of Current Science and Technology at the Museum of Science in Boston, part of the Boston community for over 175 years. For more information, visit our website at www.mos.org/CST or email us at podcast@mos.org. Thanks for listening.